day. We had talked about different types of forces, free body diagrams, and I am recording in the AM. Yes, I am. Physics 30 in the AM. Newton's laws of motion. You have this, but let's read through it. Hey, just a second. I'm going to pause for a second. Okay, Newton's first law of motion is important. If an object maintains constant velocity unless acted upon by an unbalanced force, a non-zero net force. Sometimes called Galileo's law of inertia. One property of matter is its inertia, its tendency to remain at a constant velocity. Matter is inert to change as far as motion velocity is concerned. Now, you intuitively understand inertia, which, think about football. If you're 250 pounds and you're running into somebody else who's 150 pounds, which is conceivable on a football field, who has more inertia? Who is less likely? Who's going to plow over the other guy? Yeah. And you don't even have to be going as fast because it's a combination of mass and your speed, right? Same speed, but velocity, actually. The direction is important in that case, right? You guys understand that. It's harder to stop the motion of a massive object, right? It possesses more inertia. Now, what I was showing with the seatbelt video first, I think we all understand the inertia. I think a demonstration of its comments. It's pretty simple. We know why you wear a seatbelt. It's because if you hit something, you don't want to go flying through the windshield because your velocity will still be going, right? And you guys understand that. And we've all had a little situations where you feel it on your lap. Hopefully you haven't been in any major accidents, but, right? Okay. So you guys have these questions here, stuff, and that's why I printed them out. We're not worried about the second law yet. I need you guys to think about Newton's first law to explain why steel barriers usually separate the cab of a truck from the load. You see that steel barrier in the picture, right? Essentially, there's no seat belts, but they have straps on these things. You know, and generally a load is strapped down, but just in case, talked about that. Trucks carrying tall loads navigate corners slowly. It's a tall load, even if it's a heavy truck, they tend to anyways. And customers who order takeout drinks are provided with lids. You don't generally get a coffee from Tim Hortons. What's another place you get coffee from? Starbucks, McDonald's, whatever. Anyways, you get a lid. Usually. I take it off though sometimes because it's too bloody hot, right? But then I curse myself for taking off the lid because, yeah, it spills. Okay. Come up with sensible answers for these right now. You got, this is a 3 questions, 3 minutes max, okay? You could do it on the paper, on the back of the paper, like the handout. Yeah, I heard some things talking about some people, I heard some things that people were talking about. So steel barriers. It's pretty intuitive. Why are they there? Somebody from this side of the classroom. Yeah. Somebody, come on. Why would you have steel barriers as shown there at the front of the, yeah, if you hit on the brakes hard, those straps, if the load, the straps loosen and stuff like this, the load could come up and slide right through and impale the cab driver or whatever, or like the guy in the cab. All kinds of possibilities. So it's just another layer of protection. You ever see, if you're driving through mountainous areas and stuff like this, you ever see a couple things? They sometimes have signs about pull over to check brakes. You ever see that, right? You may not notice. And they also have ensure your load is strapped down. Sometimes you'll see signs like that, and that's anything that's strapped down does loosen up over time. So it's a reminder, but especially on mountain roads and stuff like this, where they're going to be slowing down, speeding up. You don't want things flying. Also, you're going through the Rockies. If you've ever driven through, I don't know if it's the Alberta or BC side or maybe a bit of each. Going through the number one highway is what I'm familiar with, driving to Kelowna or something like this. You ever see a runaway lane, if you know what I'm talking about? Okay, you're going down a steep lane. What is that for? It's not for the average car, it's for a semi. And what happens? It's in the, yes, if your brakes are failing, I guess you could in a car, but it's more for semis that have heavy loads, a lot of inertia. They can't brake that fast, and they realize that they'll go into the runaway lane and it'll go up steeply and slow down with the gravel, etc. They'll probably have some damage because it's not a paved road or whatever, but I mean, it's not going to kill people. Is the whole purpose, right? So those kind of things. This is all related to that same law. Once you're in motion, you tend to stay in motion unless acted upon by an outside force, and vice versa. If you're stationary, which is your speed is zero, your speed won't change unless acted upon by an external force, unbalanced force. Trucks carrying tall loads navigate corners slowly. So this is top heavy. What's the reasoning behind that? Yeah. Couldn't quite hear you, but I think when it's turning, I heard and stuff like this. Yeah, louder. Oh, you're demonstrating. Okay. Oh, okay, yes. So, I think we all intuitively understand. Now, I'm sure you did it a lot better. But anyways, when you're twirling around a corner, stuff like that, maybe your speed is staying the same, but you're changing directions, and that's a form of acceleration. Um, and you will fly, like you understand this going in a circle, you have that feeling of a pull to the outside, right? Well, the load itself will tend to just want to go in a straight line. So they slow it down so there's not as much fictitious force, the centrifugal force or whatever. We'll talk about that later. And so, yeah, it'll stay in motion in the same direction unless you go slow so that it can just gradually change. Okay? You can't flip a truck if it's top heavy. It's going too fast. And lids. Why do you have lids on takeout drinks? I don't actually have a lid here, but it's because I drove here, right? What? It doesn't spill because as long as I'm going, like in an airplane, if I'm going a steady speed, generally in airplanes I don't have a lid. If you're going a steady speed, it shouldn't. We are going a steady speed right now. The Earth is rotating and traveling in space around the sun over this next year, right? And I don't have any, it's as long as you're not stopping or starting, right? So if I'm in a car traveling steady speed, it's fine without a lid. As soon as the brakes are hit, abruptly especially, the liquid in my cup will keep going at that 100 kilometers per hour, let's say you're traveling, right? I slam on the brakes. The water or coffee in my cup will still be going at 100 kilometers per hour and will fly ahead, right? The lid just prevents it from getting on your lap, your windshield, whatever, right? Okay. It's pretty intuitive, this first law. The second law of motion is mathematical. The sum, you guys are familiar with the Greek sigma, that symbol before the F? This, if you took people in foundations math, you guys see this too? You're in foundations, right? No? Oh, right. Foundations people, anybody? You guys use sigma in foundation? Yes. It just means add up, sum up. It's not difficult. Right. So the sum of all forces with direction being important, is equal to the mass times the acceleration. Acceleration is a vector too, so I put an arrow up above it to remind you. The direction is important. Okay, and we know from the units, a Newton is the unit of force, and that is a kilogram times the acceleration meters per second squared. So the units work out that way. We just use a capital M instead of meters per second squared. We use free body diagrams to analyze the problem. Okay, so we're probably going to do a bit now. And you know what? I forgot to erase the next page, so I'll just do that immediately. Here we go. Examples. Clear 8 from page. I'll give you guys a second to copy this down, and we will do it together. I'll pause the video.
Still recording? Yep.
Okay. Examples. So, force of gravity on a wagon, I already calculated the mass times gravity. Okay? 230 down. Force of friction between the tires and the ground is 10 newtons, we're going to say to the left. Sheila's pulling the wagon with a force of 15 newtons to the right. Draw the free body diagram and determine the net acceleration acting on the wagon. We're going to use this new law, the sum of all forces. So I'm going to draw a horizontal surface, because we're assuming the ground is, didn't say it's on an incline or hill. I draw a box, free body diagram. That's my wagon. I don't need details. I don't need wheels and stuff. So the force of gravity is down. 230 newtons. Now, I'm not going to put down on here. I'm going to just put negative 230. It does not say that the wagon is falling in free fall. So what do we know automatically is equal and opposite? What do we call that force from yesterday? You all know? Call the normal force. It's 230 up. It does so. Guys, does appreciate. Okay. So that's my y-axis. Now, I'm going to do a different color for the x-axis. Jill is pulling the wagon with a force of 15 to the right and the friction is 10 to the left. So I'm going to draw a smaller arrow. This is not drawn to scale. My 230 is way longer than it should be. So let's say f, small f, is negative 10. Because the norm is left is usually. And positive 15, so I'm going to make it slightly longer to the right. Force, applied force, or P if you want to say a pull. I don't care if you put P or A for a pull. 50. That's the free body diagram. Now, there's two axes that we have, an x-axis and a y-axis. We're going to do two separate forces in the x-axis. No, I'm going to do the y-axis. Now, I'm going to make this assumption, and I think you guys are familiar with this. X is horizontal, Y is up and down. Okay. So that's our assumption. If you're using anything different, make sure you write them. You don't have to write this X, Y axis on. That will always be our assumption, but there's going to be some times when you're on a slope, and I will say, do draw X and Y axis if you're at an angle and you put here that this is 30 degrees or something. That's not the case here. When you get to that. in the y-axis, oh, son of a sequence. There we go. The sum, I'm writing down Newton's second law. Sum of all forces, and I'll put a little y, is equal to mass times acceleration in the y-axis. I'm putting a little y to do for mine. I just put that equals m. Now, we have the two forces, Fn and Fg. I'm going to just put them down here. I think the math is pretty easy, so you can jump straight to 0. I'm going to put it down. The positive 230.
Sorry for the interruption, but any grade 9 and 10 junior girls interested in playing basketball, please come to a meeting in Mr. Kuz's room at lunch. That's any grade 9 and 10 girls interested in playing basketball. Thank you.
This tell us the sum of forces on the left, right? I've subbed in for the sum is 0, right? We knew this intuitively. But 0 is equal to mass times acceleration. The acceleration is 0 though, because we know there is a mass. We didn't figure it out. We could. We don't need to. Okay. The net acceleration acting on that is 0 in the y-axis. That's all. The x-axis is a little different. That one was simple. This is fairly simple. Now, I didn't have you work out the force of friction. I gave it to you. It's opposing the motion. Now, if you're pulling with more force than friction, that means that you're getting faster and faster. You're going to be accelerating. And we'll see how much the acceleration. So in the x-axis, I'm going to state the law that I'm using. Acceleration in the x-axis. I've told you before, I tend to make my A like a typewriter. You can make a regular letter A if you like. There's nothing special about my A. I don't care. It's not like it's a new symbol. So my sum of forces, I put my positive minus my negative. I don't double negative, I just use it. It's actually the sum of negative 15, or positive 15 and negative 10. So I just call it 10, minus 10. Mass, acceleration. Okay, you can see the arithmetic is fine. Crap. I need the mass, don't I? How do I figure out the mass? I didn't give it directly. I gave enough information to find it because we want to solve for acceleration. And it's not easy. It's not 0. So on the red, on the y-axis, I could just divide by m. Because 0 divided by 0. Right? And I don't include units with 0. You can't. Meters per second squared. Anyway. How do I figure out the mass, guys? Back from the original info. There's one thing we can assume. The 9.80 acceleration due to gravity, or we can use from the weight force, the Fg. Okay, so I'm going to go back and I'll continue on with this. And the Fg is equal to the negative mass times G acceleration due to gravity. I'm going to just sub in that we use negative 230. I'm doing it in a different color just so you can see it's sort of an insert. Negative m, what we're trying to find, times 9.80 meters per second squared. I'm big on units, so I write them down always. If you want to just leave them out and make sure you have kilograms at the end, I'm fine with that. 2 negatives, so that's just fine. I'm going to left, right, reverse the mass. and call it 230 newtons divided by 9.80 meters per second. Knowing that newtons are kilogram meters per second squared, it does come up to 230 divided by 9.8. Oh, guess I'll use this. Oh, turn it on. 230. 23-ish. 23.469. Okay. I'm going to only keep 2 sig figs. We're going to just say it's 23. Okay. Now I can go back to my x-axis. Oh, change my color to green. And say that my acceleration so I'm returning this. I'm going to say acceleration in the x-axis is equal to 5 newtons divided by 23 kilograms. You guys see mathematically where that all came from? I just had to do all this figuring. And 5 divided by 23. Apparently, I had decimal 2 on it, so I'm going to assume when I did it last week. And that would be in meters per second squared. It is positive. That means on the diagram, the x-axis is going to the right, and it's speeding up by decimal 2 1 meters per second every second. It's getting faster, faster, faster for that period of time before speed. Math-wise, you guys follow that? Now, we have access to textbooks that we're going to look at on tomorrow. And you'll see about 16 and 17. With this amount of time, I'm not going to ask you to do it. Okay? So people, I'm going to get set up with tests. And we will see from there. Okay? Over and out on the record.